So as we're going through this new chapter with carboxylic acid derivatives, I sure hope that you are seeing the strong parallels with what we saw when we went through the reactions of aldehydes and ketones, because we're pretty much doing the same order of things. This mini lecture is going to be looking at the addition of hydride reducing reagents, and then the next mini lecture will be looking at the addition of organometallics, Grignards and organolithiums. So kind of more of the same, just with a twist maybe. All right, so here's where we're at. We just learned about Gabriel and haloform reactions, which are kind of oddball little things thrown in miscellany in the middle of this chapter. But 4 and 5, mini lectures 4 and 5, are a review of stuff that should make good sense. So reductions. Let's not talk about reductions. Let's talk about oxidations first, because that's what we just started looking at. One thing about oxidations is that we learned, primary alcohols can be oxidized up to the aldehyde. But if we aren't careful and don't use specific reagents, that oxidation will keep taking place to give you the carboxylic acid. So I can go from oxidation state +1 +1 -1 -1 to +1 to +3. So I have two steps so that I can get oxidized, as we say, all the way up to the carboxylic acid. Well, the same is true for reductions. So there is some carboxylic acid derivative, which would be in oxidation state 3. I can reduce it down to the aldehyde, but reduction can take place again to go all the way down to the primary alcohol. Now, what's going on here? Well, if we have something like sodium borohydride, we know that is just, we can use H- mechanistically. So that's what I'll do to keep it clean here. So H- adds to our carbonyl, get that nice tetrahedral intermediate, and then, of course, our pi bond is regenerated. I kick out the good leaving group X-. I don't kick out R-. I don't kick out H-. That gives me this guy. Well, what's this guy? Hey, this guy is an aldehyde, a carbonyl, and something that is desperately ready to be attacked by H-. And so that is why we keep reducing all the way down to the primary aldehyde. Especially keep in mind that what you're looking at is all these molecules sitting in a sea of solvent with H- around. Where is H- going to go? Well, the aldehyde is more reactive than a carboxylic acid derivative, as we'll see in just a minute. So it's pretty much going to get reduced all the way down to the alcohol. So that was the mechanism. How do we achieve selectivity? Well, there's two different kinds of selectivity I want to talk to you about. And I'm bringing in a little bit of chapter 21. And what's on the screen right now is the chapter 21 bit. That basically, there is the selectivity of being able to look at, say, amides versus acid chlorides and realize that acid chlorides are a lot more electrophilic, a lot more reactive than, say, an amide is. And we'll go through this in great gory detail in chapter 21. But it's actually chapter 1, because what we're looking at is resonance contributors. So because the nitrogen is pumping its lone pair into the amide, well, that makes it a lot less electrophilic. But the other part of reactivity here that we're going to talk about is the fact that all of those carboxylic acid derivatives are a lot less reactive than aldehydes and ketones. Okay, so the two kinds of selectivity start with this question. Can I reduce a ketone or an aldehyde selectively in the presence of an ester? So based on what I just said, that aldehydes and ketones are lots more reactive than an ester, for example, this should be easily done. You just want to keep in mind that you're going to have to choose a hydride reducing agent that is selective for the most reactive functional group. The other kind of selectivity is this selectivity. Can I possibly reduce a carboxylic acid derivative selectively and stop it at the aldehyde stage? So just like we saw for the oxidation to the aldehyde into the acid, now we're turning the tables, if you will, and trying to figure out, geez, can I do the reverse? Can I take my carboxylic acid derivative, reduce it down to the aldehyde, and not have this happen? And the answer is yes, you can. And the answer is based on this screen. There's a whole bunch of different kinds of hydride reducing agents. Now, we've already seen lithium aluminum hydride and sodium borohydride, but there's a lot of different hydride reducing agents. There's this funky looking thing, an aluminum hydride. There's a really, geez, this is crazy looking borohydride, a borate with a hydride. What you want to look at with all of these is there's an H, there's an H, there's an H, H. This one's the H is right there, and so on and so forth. Woohoo, there's my H. Oh, looky, there's my H. You're looking and recognizing that all of these are hydrogen donors, not acids. Not acids, we're talking about H minus. All right, so the thing is, I've said, oh, just forget your spectator ion, it's just H minus. And that is an absolute lie anymore. I gotta tell you, I've just been oversimplifying like you wouldn't believe. Now we really need to pay attention to our hydride reducing agents. So, we could even have super funky, crazy hydride reducing agents like this one, where there's my hydride, and the whole thing about this one is that it's chiral, so that I can actually carry out a reduction of this ketone to this alcohol enantioselectively, and don't worry, we're not going to go there in this class, but it's very cool stuff. All right, so what about all these hydride reducing agents? Well, okay, here's the deal. We've got soft, little, mild sodium borohydride. Sodium borohydride is the little fuzzy, gentle bunny rabbit of hydride reducing agents. It's very, very, very mild. Okay, so it is only going to reduce the strongest electrophiles, the most reactive electrophiles. So that means aldehydes and ketones. And maybe you can get it to reduce the highly reactive carboxylic acid derivatives like acid chlorides and hydrides. Okay, what about lithium aluminum hydride? Well, holy cow, that is like, I will reduce everything in sight. It is kind of the bazooka of hydride reducing agents. This is where the story of Sven comes in. Lithium aluminum hydride is just blow your carbonyl out of the water. Okay, so it will reduce everything all the way down. everything will go down to the alcohol. Or if it's an amide, it'll go down to the amine. So what about those other funky reagents? Well, the funky reagents that are in Chapter 20 are DIBA or DIBAL, diisobutyl aluminum hydride, and this lithium tritert butoxide aluminum hydride, and those are just kind of complex designer reagents, just like we designed PCC in the selective oxidation reagents, that are designed to be able to achieve that selectivity of stopping at the aldehyde. So very cool. So these two take us from RCO2X, an ester or acid chloride or whatever, down to the aldehyde, and then we are done. Why do they work? Well, the reason that DIBA works is because you can run the reaction at minus 78 degrees. So what you'll see happening is that your H minus, and again, this is kind of cheating. It's more than just H minus, but we get our tetrahedral intermediate, which we see on the right here. Here's the H minus I just added, and the aluminum ends up coordinating to my O minus. So here is that aluminum oxygen bond. So that's the intermediate, the tetrahedral intermediate that I make. And that intermediate is perfectly stable at minus 78 degrees. So as long as you keep this reaction at minus 78 degrees, which is easily achieved by putting dry ice in an acetone bath, this breakdown to kick out the ethoxide and give you the aldehyde, that doesn't take place. And if the aldehyde isn't there, then it can't get reduced anymore. So how do you get the aldehyde? Well, you get the aldehyde by adding water and acid, an acidic aqueous workup, to the reaction mixture while it's still cold. All right, so the point is, while it's still cold, you're adding this stuff, and the water and acid is reacting with your hydride right here and quenching it. So I have no more hydride left. There's no hydride. What is happening to that intermediate is I'm protonating the alkoxide. So I've gone to this let's see, what is that? Hemiacetal. And the hemiacetal, as you know, is in equilibrium far, 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 far to the right with the carbonyl, the aldehyde. So there's no H minus left. It's been quenched as shown right here, and the whole success story is because you've made this intermediate that is stable at minus 78 and doesn't break down to give you the aldehyde. So that's one reagent. The other reagent is this lithium tritert butoxide aluminum hydride. And why does it work? Well, what you can see is that, man, it's kind of a bulky reagent. So it is pretty much slow to react. So when I try to add my quote-unquote H minus to my acid chloride, again, I'll get that intermediate, and that intermediate may react to, kick out the chloride to give you the aldehyde, but it's just so slow to react at minus 78 that as you monitor the reaction, you can stop right here and quench it before the second reduction takes place. So I can stop this just because my hydride reducing agent is so sluggish in reacting. So I'll just watch my reaction when all of the acid chloride is gone and I've got all of my aldehyde. I say, okay, I'm going to add my acid and water now and work out my reaction and isolate my aldehyde. So those are our selective Hydride reagents. They both work quite well. Now, the $20,000 question. What do you call 50,000 geeks playing Monopoly? Give up? But of course. See you in class.